Oh. Come on. The monitor's got to wake up.
I woke up at 6 o'clock this morning and it was smart. Yeah, you gotta do what you gotta do.
There we go.
Because I stayed up till like 10 last night.
We are awake.
Maybe like right before midnight.
All right, everybody, let's get started. How did the assignment go yesterday? The one that required a bit of iteration. The one that I'm assigning today should not require iteration. And if you would like a little bit of better news than that, oh, that's a typo, because that's supposed to be 2, 3, and 4. So I'm assigning a homework today that's due Friday. Would you like to hear that I'm not giving you one on Friday due Monday?
Yeah.
Sorry, I thought you'd like that. Okay. I want to show you something else because we are actually getting a little close to this. Let's see. So, wait, oh, wrong folder. So we are getting close, actually, already to our second exam on connections, because we start welds on Friday. This decides to wake up. Okay, so, all right. So today is Wednesday, February 26th. We're closing out bolts by looking at slip critical connections today, which I think you'll find in practice are pretty straightforward. If you understand everything we've done so far, this is just a slight little add-on to that. We have 1 week of welds. So we're going to be doing fillet welds Friday, Monday, and Wednesday. Then, so the way I've structured this, Friday next week, not like 2 days from now, but 9 days from now, we review for the second exam, okay? We have our second exam Monday, March 10th, okay? We're going to come back on Wednesday. We're going to have one lecture on columns, sort of our background theory-based lecture on columns. What I'm going to do is I'm going to give you a homework that's due Friday. But we're not going to have class on Friday, and then you have spring break. Does that sound good? So, in previous semesters, we were able to end connections and then go straight to spring break. But because of the new calendar this semester, we sort of have like a week left over. So I kind of want to do this lecture on Wednesday, but then Friday I'll give you off. So, sound good? And this is like an Excel-based homework too, so it's pretty straightforward. So, then when we come back from spring break, we can get right into column analysis and design, get into beams, and close out the class. Sound good? All right. Everybody get this? Okay. Let's get to slip critical connections. Okay. All right. So here's the thing with bolted connections. So we said that there were 2 classes of bolted connections that we need to assess, and that is a bearing type connection and a slip critical connection. Okay? Now, a bearing type connection must satisfy 2 limit states. Okay? So what are those 2 limit states? The bolts must provide enough capacity so that they don't fail in shear, and the plate must provide enough capacity, or plates, plural, such that the plates do not fail in a bearing type phenomenon, because the bolts come into contact with the plate, and the plate can either tear out or the hole can plastify through bolt hole ovalization, right? Okay? And so those are our 2 limit states for a bearing type connection. For a slip critical connection, this doesn't change. We still have to satisfy bolt shear and bolt bearing. With a slip critical connection, we have a 3rd limit state that we add, which is slip resistance. Okay? And so, and we do still have to meet our layout requirements as well. Okay? I want to be clear that we do have a 3rd limit state that we need to assess, but not only does the analysis not really change, but really the design process doesn't change either. So how do we design a bolted connection? We determine the load that we're designing for, which could be a design to develop full capacity type load, but so far it's just been a factored load. Okay? We determine the shear capacity of an individual bolt. I'm going to tweak that a little bit and say, now for slip critical connections, this is the only step that's going to change. Okay? So for a slip critical connection, instead of determining the shear capacity of a bolt, we're going to determine either the shear capacity or the slip capacity and just take the smallest of the two. Okay? So what we've got to do is figure out how to compute slip capacities, which is pretty straightforward. And then what do? Get the required number of bolts, lay out a pattern, check bolt bearing, iterate. Okay? So did everybody, like, was homework 3.3, was that pretty straightforward? So if you understood that, then I think what we're going to do today with slip critical connections is really going to be pretty easy. Okay? So let's talk about a slip critical connection. How do we analyze and design it? When would we use it? So on and so forth. Okay? So let's just sort of think in our heads about what happens when we bolt two pieces of steel together. Okay? So we have plate A, we stick a bolt through them, and we tighten the bolt. Okay? What happens to the two plates as you tighten the bolt? They smack together, right? Okay? And would it be fair to say that the more you tighten the bolt, the more those two plates are going to want to be mashed together, right? So if you really wrench on that bolt, you're going to get a lot of force between those two plates, right? So if I tighten the bolt, would it be fair to say that I'm going to develop a force between the two plates that's acting normal to the plate surface, right? So think about it like this. Let's say this is a plate of steel, right? Okay, and I have a big force that I'm applying downwards, okay? And then let's say I've got a box that I'm applying downwards. And then Jimmy grabs that box and he starts yanking it this way. What's going to get in his way? Friction, right? Okay, so how do we calculate that frictional force, right? It is a normal force multiplied by a coefficient of static friction, right? Mu times some normal force. Y'all remember that from statics or physics? Same idea here, okay? So the difference between a bearing type connection and a slip critical connection is as follows. Bearing type connections resist load through that contact between the bolt and the plate, right? And so it's either the bolt fails or the plate fails. But in a slip critical connection, we account for that friction, okay? So in order for this to work, okay, we have to develop that friction, okay? So in a bearing type connection, we're just getting the bolts snug tight. In other words, get them, in contact, get them put a few hits on an impact wrench or, just like the full effort of an iron worker, and that's snug tight. Slip critical is different, okay? Slip critical is we get the bolts snug tight, and then we have to utilize a specific defined method to achieve an appropriate torque or an appropriate pretension, okay? Now, I'll talk about those methods here in a bit and the goals, but the point I'm making is that in a slip critical connection, the bolts are not snug tight. They are tightened to a prescribed torque to generate a certain amount of normal force. Generate that normal force, we get the pretension, or we get the friction that we can rely upon. Does that make sense? Now, when would we use a slip critical connection? Two instances come to mind. Slip critical connections are commonly applied in earthquake scenarios, okay? And they are commonly applied in bridges, okay? Bridges are subjected to cyclic load, so they're loaded, unloaded, loaded, unloaded, loaded, unloaded, and so that required amount of tension is necessary. To give you kind of an idea of what I'm talking about, this is a little bit unrealistic, but you'll kind of get the idea. Imagine that, how many of you have ever mowed a lawn before? Okay, so what would happen if you were mowing a lawn and the bolts were not fully tightened on the lawnmower? They would just sort of loosen off and fall off, right? So the idea in a bridge is that we want to get those bolts to a certain tightness because they're going to be loaded, unloaded, loaded, unloaded, and we don't want that to fall off. That's not a totally straightforward explanation, but that can give you kind of an understanding as to what we're concerned about in bridge land and whatnot. Okay, so first thing I want to talk about are the different methods in the field that you can use to generate this prescribed pretension. This is probably one of the most common. It's called the turn of the nut method. I am curious if anybody in here did any summer internships with the DOH and saw anything like this on any bolted connections. Does this look familiar? Okay, so this is the turn of the nut method. So the idea behind the turn of the nut method is you get the bolt snug tight, and then what you can do is you can look up the appropriate amount of torque for a given bolt. And the way that the spec reads this, and by the way, you can find this in the manual. It's actually behind the commentary. It's on 16.2-63. But basically, based on the given conditions for your connection, you'll say, okay, a third of a turn past snug tight, or half of a turn past snug tight. And so what they'll do is they'll mark the plate, the bolt, and the nut, and then they'll turn them to where they're lined up, okay? This is a fairly standard, straightforward approach for achieving pretension, and it works very well. And by the way, let's talk about pretension, because I've been using that term a little bit. I'm going to talk about it a little bit later, but let me take a sidebar and talk a little bit about pretension. So the way that we specify the amount of torque necessary in a given bolted bolt assembly is through pretension, okay? So let's think about this like it's a statics problem, okay? So here's plate A, plate B, stick a bolt through them, right, and tighten the bolt, right? What's happening to the plates? They're being smacked together. So is it fair to say that the bolt or the plates are being subjected to compression? Does that make sense? Where does that compression come from? I'm taking the bolts and I'm tightening them, and I'm really wrenching on those things. What is happening to the bolt inside that assembly? That bolt is experiencing tension, right? Okay, the bolt is experiencing tension. If that's kind of a hard thing to wrap your head around, this is an easy way of thinking about it. Okay, so let's say that I had a rope sticking out of this wall. So there was like a hole, and I had a rope sticking out of the wall, right? Okay, and I've got the rope, okay, and I want to perform an action that will apply compression to the wall. Okay, so how am I going to do that? Maybe what I'll do is like that, right? Does that make sense? So what am I doing to the rope? I'm taking the rope and I'm applying tension to it. Does that make sense? So the way that I lock that compression into the wall is I apply tension to the rope, right? How many of you have heard of pre-stressed concrete? So here's a 30-second explanation on pre-stressed concrete. Concrete is a material that behaves very well in compression, but very poorly in tension, right? Its tensile strength is about 10% of its compressive strength. Now, in reinforced concrete in CE413, what Dr. Zatar will teach you how to do is put rebar in the tensile regions to counteract concrete's weakness in tension. That's reinforced concrete in a nutshell. The way pre-stressed concrete works is we take elements of steel and we lock in a tensile force inside the steel, inside the member. So the tensile elements are stressed, and then the concrete is cast. And there's all sorts of things about whether they're pre-tension, post-tension, you know, we can talk about that. But the idea is by locking in a tensile force inside the steel that results in transferring a compressive force to the member, right? And we typically do that in the tensile regions because if we put a locked-in compressive stress inside the member, that makes the member behave better. So we can use smaller, more slender elements for longer spans. That's pre-stressed concrete in a nutshell, by the way. So that's kind of the idea. So this term pretension, when I use the term pretension, what I'm doing is I'm saying we're trying to specify the amount of tensile force that needs to be locked inside a bolt in order to generate slip critical capacity. That tensile force is about 70% of the bolt's full tensile capacity. So if you hear me use the term pretension, that's what I'm talking about. the goal with these methods is to try and hit 70% of the bolt's tensile capacity. And by the way, not only do we hit 70%, but on average we hit more than 70%, and you'll see what I mean. Actually, it's about 13% more, and you'll see what I mean here in a bit. Okay. Okay, so the first method the most common method you'll see in the field is turn of the nut. And again, we had a couple students who've been on DOH sites and seen that. Another method is to use just a calibrated wrench. So if you're ever on a site and you see one of these like clipped to one of the columns, this is, for example, this is a common brand. This is a Skidmore Wilhelm. Basically what this is a super duper hyper accurate bathroom scale, but meant to measure the amount of pretension generated by a calibrated wrench. So the idea is you would stick a bolt through this and run your wrench to ensure that you're getting the appropriate pretension. Once the wrench is calibrated, you can then just start using that in the field. Okay, so that is an option. Okay, one of the downsides is you do have to calibrate that wrench daily as you're working on the job. So you go to work the next day before you start installing slip critical bolts. You got to make sure it's calibrated, and you have to keep doing that repeatedly. So it's just I guess a labor-intensive issue that you need to be aware of. Okay, twist-off control bolts. Has anybody on a DOH project seen these before? You've seen these? Oh, okay, good. Okay, good. So a twist-off control bolt. These things are actually really cool. They're kind of magical in that they are really fast to install. I kind of like twist-off control bolts just in general, regardless of their slip-critical aspects, because of how they tighten. Okay, so if you look at a standard bolt, you know, something like this. Okay, actually, let's look at this. Okay, so how do I tighten this? Okay, I need a wrench on this side, and I need a wrench on this side, right? Now, if I have a girder that I'm trying to splice together, and that girder is, I don't know, 6-7 foot deep, I can't exactly do that myself, right? I got to have somebody on this end and somebody on this end. So it requires two people, right? Or somebody with a wrench on one end, somebody with a wrench on the other end. You can't do that by yourself. But with a twist-off control bolt, you can, okay? So the twist-off control bolt has a slightly different geometry, okay? So first off, one of the things you'll notice is that the head of the bolt is round, okay? It's not hexagonal because you don't need a wrench on the far end, okay? The way that it works is the twist-off control bolt has a standard nut, but the bolt has this like splined end, okay? And the wrench that you use grabs the bolt assembly only on one side. So it grabs the nut, and then it grabs this splined end, this little nub on the end of the bolt. And so when you tighten, it spins the bolt and the nut in opposite directions. So if you have a bolt right here you're trying to install, you only need a person on one side. So they're very labor friendly in that it doesn't take a lot of labor to install a given bolt. The other thing is it makes it really easy for inspection standpoints. So for turn of the nut, an inspector is going to come through and make sure that all the marks match. But in the case of a twist-off control bolt, once the bolt achieves its appropriate pretension, this little splined end chucks off, it shears off. So all you have to do is look for a connection with the little nub off, and then you can see that the bolt achieves its required pretension. So it's really we're really labor friendly. The bolts themselves are much more expensive, but the savings come from labor. Fourth method that I want to mention are what are called direct tension indicators. A direct tension indicator is really just a fancy washer, okay? The washer has these little like nubs on it, okay? And the idea is that as you tighten the bolt, this washer will sort of mash down, okay? So like this is before and after, okay? And if in order to achieve your required pretension, you have to have that mash down to a certain gap. There's these feeler gauges that you can use, and if it doesn't fit in, then you know it meets pretension. There's also a product where the washer has these little nubs, but on the other side, there's like this like orange goop. It looks sort of like almost like Play-Doh, and then as you mash this down, as you tighten the bolt, once you achieve that pretension, that goop sort of squirts out, and so when the goop starts squirting out, you can see you meet your pretension. So this is an area in steel design where there's all sorts of different products to make the installation that much more user-friendly, if that makes any sense. Okay. Does this make sense? Okay. Now, capacity, okay? So how do we compute capacity? Okay, the first thing I want to do is sort of call your attention to just basic physics, right? So what is the lateral force from friction that we can calculate? Well, it's going to be a coefficient of friction times the normal force, okay? So the way that we compute the capacity of a slip critical bolt is we say, okay, we take the coefficient of friction times the normal force, but then there's a bunch of correction factors. So it's basically the standard equation that you would have from an undergraduate physics class, just modified a little bit, okay? Excuse me. One thing that's a little unique, and I think there's only one other instance that this happens this semester, is the phi value is 1, okay? Because this is typically treated at sort of a service level load type situation, so the phi value is 1. That's not a mistake. That's what we'll use, okay? So let's see if we can start chipping away at what each of these terms are. So first off, the phi value is 1, okay? Rn, so phi Rn is just our nominal resistance, okay? So what do we have in here? We have mu. Mu is our mean slip coefficient, which is basically our coefficient of friction, okay? Now d sub u, if you look up d sub u, it will just tell you the d sub u right here is just 1.13, okay? And so some of you, so that raises probably a couple of questions. First off, what is d sub u? Like, why is it there? Okay, so let's talk about what d sub u is and why it's there. So remember I told you that our goal is to achieve 70% of the bolt's tensile capacity, that's our bolt pretension. And then I showed you a bunch of methods. I showed you twist off control bolts, turn of the nut, all that, right? What happens is, so we're trying to achieve 70%. If you were to actually go and measure the amount of pretension that you get in bolts in the field, you end up getting a lot more than 70%. Well, not really a lot more. On average, how much more do you get? About 13%. In the field, the methods that we use end up generating, on average, more pretension than we want, and so that we can actually account for that in our computations. So d sub u is a multiplier, and it reflects the ratio of the mean pretension that you get installed in the field versus specified bolt pretension that's specified in the spec, okay? And the reason that it's not just a constant, like that it doesn't say 1.13, that it just says d sub u, is that the EOR could actually use a different value if they wanted, if approved. By the way, if I use the term EOR, what does that mean? The engineer of record. So if the engineer of record suggests or specifies or permits the use of a different value, they can. To be honest, I don't know of many engineers that do. At least most engineers that I'm aware of just go with the straight 1.13, but it is possible, okay? All right, so what's next? Okay, H sub F is a factor for filler plates. I'm going to show you what that looks like here in a second, but in most practical applications, we're just going to take H sub F to be 1, and I'll show you cases where it wouldn't be 1. You'll see what I mean. T sub B, that's our normal force, okay, and that's our minimum pretension. That's our pretension that we're getting from the bolts being tightened together. And then N sub S is the number of slip planes. So this is what all these terms are, and then let's see if we can dig into maybe a little bit more details on what each of these values are. So let's start off with the mean slip coefficient. So mean slip coefficient, that's your coefficient of static friction. What the manual does is we characterize our coefficient of friction based on the condition of the surfaces that are being connected. And so the manual lists 2 surfaces, Class A and Class B. There are slightly different specifications in the AASHTO bridge spec, but for the most part, the idea is kind of the same. So, so basically what we're talking about is the condition of the surfaces that are being in contact. In most cases, we're going to assume Class A surfaces. It is possible that if you do a little bit of work on maybe blast cleaning the steel, that you might be able to get Class B. But unless otherwise stated, we're going to assume that the two surfaces that are in contact meet Class A. And if that's the case, then our mu value is going to be 0.3. Okay, so that's our coefficient of friction between steel on steel. Okay, so, and honestly, if you open up a statics book or a physics book, you'll probably find that meets the range that you'd find in a conventional textbook anyways. Okay, does that make sense? All right. Okay. What about the bolt pretension? The bolt pretension is a lookup. Okay. This comes from table J3.1 on 16.1-36. Really straightforward. So all you do is you look at your bolt diameter, what group you're in, and there you go. So if we had a 1-inch bolt that was group 120, we would try and achieve a bolt pretension of 51 kips. Okay? And don't worry, we're going to have a quick example going through these calcs here in a bit. Okay? So I'm going to skip past this because we're going to look at it here in a second, but it's a pretty straightforward lookup. Okay, filler plates. This is a little bit difficult to explain, but I've got here an image on the board or on the slide, which is a little noisy. So I'll try and I don't know, like simplify that a little bit. So for those of you that have been on like DOH bridge sites, those connections I was talking about, most likely we were looking at maybe a splice connection where you had beam A and beam B that were being connected together. If you want an image or an idea of what I'm talking about, how many of you have seen here recently on Interstate 64, if you're going eastbound towards Charleston, right there near the mall, you see that they've got those girders there that have been sitting there on the side for a little while. You can see the splices that they've got connected where they're going to splice beam A to beam B. Does that make sense? Okay. So quick and dirty sort of idea of what we're talking about. All right, so here's the beam, right? We put load on it. So what's the moment diagram look like? Something about like that, right? Okay, so where are the biggest moments? The biggest moments are here in the middle, right? Now let's say that this bridge is, I don't know, like 150 foot long, okay? So we're not, or no, let's make it like 200 foot long. Let's make it really long, okay? We're going to need a bigger beam here in the middle than we are here on the ends, right? Okay? So if I wanted to be a little cartoonish, like if I were to actually look at the steel beam, in the middle, we might have a beam. Actually, hold on. Sorry, I'm trying to be cartoonish. So in the middle, we might have a beam that looks like this, but then on the ends, we might have a beam that looks like this. So like here's our support, and then we'll have maybe something like this. So in other words, the beam has thicker flanges in the middle, right? Because the moments are bigger in the middle. Does that make sense? Okay, so now I need to connect these together, right? So, okay, so how am I going to connect this right here? Okay, so maybe what I'll do is I'll have a plate, you know, like this, put some bolts, you know, like that, right? And then what I'll do is I'll want to connect the flanges, right? But the problem is this flange is thicker than this one, right? So what I'll do is I'll smack a little, like, filler plate right here so that when I try and splice them, that it's flat. Does that make sense? So that's what I mean when I say a filler plate. So if you look right here, you can see, so this, like I said, that's cartoonish. This is a little bit more realistic. So this is me trying to splice beam A to beam B. And so you can see here's the web, flange, flange, web, flange, flange. And you can see that the plate is, or the flange is thinner on this side than it is on another. So in order to get a flat surface, we stick this yellow filler plate in the middle so that everything meets up flat. Does that make sense? Okay. Now, That's what a filler plate is for, okay? So this is why the filler plate factor is usually 1, okay? If you don't use filler plates or you use one filler plate, HF is 1. The only time that HF is smaller than 1 is if you were to use 2 filler plates, okay? And some of you might be thinking, well, gracious, like when would you need 2 of these things? Well, you would need 2 of those things if your difference in thicknesses is really weird. So, like, for example, if you had a difference in thickness of 3/8, maybe you use one plate that's a 1/4 inch and one plate that's 1/8 of an inch, right? So that it matches up to be 3/8. Or if your difference in thickness was, I don't know, like 5/16 or something, like a 1/4 of an inch and a 1/16 of an inch, like some sort of like weird fractional difference where you needed 2 filler plates. But in most cases, that's pretty rare, okay? So like I said, the vast majority of like practical applications, we would take H sub F to be 1. Does that make sense? Okay. And by the way, oh, I should, sorry, I did mention one thing. The number of slip planes, that's just the number of shear planes, right? So if you had multiple surfaces, you'd get multiple friction. Okay. So let's do a quick exercise. So what is the design slip resistance of a 3/4 inch diameter A325 bolt or group 120, assuming Class A fang surfaces and 1 slip plane with no filler plates? So again, the math is really easy. Okay, so let's see if we can walk through this. So okay. So the expression that we're going to use is that, okay? And then, from that, we'll calculate phi RN. All right? So, and actually, you know what? Maybe I ought to use little r since we're looking at per connector, but we'll do that here in a bit. Okay, so our phi value, remind me, what is phi? 1. Mu, okay, so if it's a Class A fang surface, what's our mu value? 0.3. Du is 1.13. HF is 1.0. TB, okay, what is our bolt pretension going to be if we have a 3/4 inch diameter bolt and a group 120? Okay, so that's going to come from table J3.1. What is that? 28. He's got, I saw he had his manuals. That's 28 kips. And NS is 1. Okay? So, therefore, phi RN, like we're basically just going to multiply all this. So it's going to be 1, 0.3, 1.13, 1.0, 28 kips, 1.0. So what is that? 9.492. So we'll say 9.49. Is that difficult? Okay. Do you remember how, with bolt shear, remember how we did an exercise very similar to this, and then we said, okay, here's how you compute bolt shear capacity, and then we're never going to compute it again. Y'all remember that? Okay. So let me show you something. All right. All right, so here's the manual. And then okay, I want everybody to turn to this. Everybody turn to table 7.1. This should be familiar, right? This is table 7.1. Now I want you to turn the page to table 7.3. So what do we have here? Slip critical connections, group 120 bolts. Okay, so what do we have? We had group 120 bolts, class A fang surface, standard, so over here we have standard holes, oversized holes. This is where it says SSL and SSL and along LSL. This is a short slotted hole, long slotted hole. This is transverse loading, parallel loading. We're just going to look at a standard size hole, single slip, 3/4 inch diameter. What do we get? 9.49. It's a lookup, right? So table 7-1 is your bolt shear capacity table. Table 7-3 is your bolt slip capacity table. Okay? So you don't need to, you can just look it up. Okay? Is sort of what I'm getting at. Like I said, we'll do the calc and then we'll never do it again because we can just look it up. Okay? Does that make sense? I'm hoping that this is a pretty straightforward calculation. Okay? All right. So far, so good? All right. Let's see if we can work through some basics of a given problem. Okay, so like I said, here's the bolt slip capacity table. I will say a couple things. If you have a Class B fang surface, just multiply whatever's in this table by 5/3 because Class B is 0.5, Class A is 0.3, so just 5/3. And then you can have single shear or single slip or double slip. Okay. Let's see if we can do a quick design example to see if we can work through how we would design a connection if it was slip critical. And again, I think you're going to find this is pretty straightforward, okay? So, not really very challenging, okay? Like I said, if you can do a bearing type connection design, I really don't think you're going to find this is out of the mark. I think you're going to find this is pretty familiar, pretty straightforward. So we're going to design a slip critical connection to withstand a dead load of 65 kips and a live load of 115 kips. We're going to use group 150 3/4 inch diameter bolts, A572 grade 50 seal, and minimum spacing. And by the way, we might not finish this problem, but we'll at least get to a point where we can lay it out. Okay. So what's going to be our first step? Factored loads. Yeah. So that's just going to be 1.2 dead plus 1.6 live. Which, that's going to be what, is that 262? That should be pretty straightforward, okay? The only part of this problem which is substantially new is the second step, okay? So, okay, so let me explain what I mean by that. Before, what we would do is we would say, okay, here's the load, here's the shear capacity of a bolt divided to get the number of bolts. Now what we're going to do is look up the shear capacity and the slip capacity, and just take whichever one controls, okay? So let's look at bolt shear first. So for bolt shear, okay, what do we need to know in order to be able to assess bolt shear, in order to calculate or to look up the capacity of an individual connector? Maybe start off with the group. What group are we going to be in? 150. Did I say anything about threads included or excluded? So what do we do? There we go. What else do we need to look up a capacity of a bolt and shear? We need a diameter of the bolt. What's the diameter? And is there anything else we need to know? Single shear. This is a single shear situation. All right. So what I'm going to do is I'm going to call that phi RN V. Phi RN for shear. What is that? Say it again. 22.5 kips per bolt. Okay, is everybody else seeing that? Okay. Now let's look at bolt slip. Okay. Okay. So we're going to be group 150. By the way, I'll throw some notation at you. If I ask you to design a connection using group like 120 or 150 FC bolts, that implies you're designing a slip critical connection. So just the group, should be pretty straightforward. Okay, what about our bolt diameter? We're going to need that. That's the same. Single slip. And then, did the problem say anything about our fang surface, Class A or Class B? Did it? So when it doesn't, what do? Assume Class A. At some point, I need to get in the habit of not explicitly saying every parameter, because at some point, you do have to start making assumptions. So, okay.
If it is a single shear, does that mean it's single slip?
Yes.
Okay.
Yes. Okay. So if this is the case, what is our phi RN? So what I'll do is I'll say phi RN SC. So what is that going to be? If we have a group 150 bolt that's 3/4 inches in diameter and single slip under Class A, what is our capacity per bolt? 11.9. Okay, everybody else find that? Okay, good. Now from these two, if I'm designing this connection, which one would I use for design? Bolt slip. You would use the lower one, right? Because if I have to use a value for design for a given bolt, do I count on 22 kips per bolt or 11 kips per bolt? I count on 11 because that will result in a connection with more bolts, right? Which will be more conservative, right? So past this, the problem is pretty much going to be, what you would expect, okay? So what do? calculate the required number of bolts, which is going to be our load over the capacity of a single bolt. Our load was 262, and that's going to be 11.9. When you chug this out, you're going to get 22 point something volts, like 22 and change. I think what I would do is use 24. And I think what I used for a trial layout is the following. So first off, our S-min is 8/3 times the bolt diameter, which is 2 inches, and this is a lookup, which is 1 inch. And keep in mind, our plate is only 9 inches wide. So what I'm going to suggest that you use for a trial layout for a problem like this is the following. Okay, so 24 bolts, where this dimension is 1 inch. And these are 2 inches, and then these right here are also 2 inches. Because, so the plate is 9 inches wide, so 2, 2, and 2 means we got 1.5 inches on either end, which meets our edge distance requirements. That's about the most contained I can make the connection for our problem. Does that make sense? All right, any questions on that? Okay, the nice thing about slip critical connections is that, so, and then I'll let you go, is, so if you look at slip critical connections versus bearing type, you typically need more bolts. I mean, because think about it, you're trying to rely on friction, right? So chances are you probably need more bolts to satisfy the same load demand. So what I'm getting at is slip critical connections usually have less of a need for iteration during design, if all we're talking about is a single, lap shear type connection, which is what we've been dealing with this whole semester. Okay, make sense? Got an assignment for you on this. This assignment is due Friday. No homework this weekend because we start welding on Friday. That's all I got, everybody.